Hi, my name is Yar Gritsuk. I am the team lead and safety pilot for the Clark College Aerospace program UAV team. This is my second year at Clark College. I've been on the team for 2 years now, and my degree with UAS Technologies prior to joining the team has been very limited.
My name is Brian Danielson. This is my first year at Clark College and also my first year with the aerospace program here. I haven't had any experience with UAS technologies prior to that. And I am the payload bay designer and the ground station controller.
My name is Jared Waldron. This is my second year at Clark College. It's also my second year on the team. I've been doing a lot of the airframe development and component manufacturing, and I will be doing repair on the flight line. Prior to this program, I had no experience with UAS technologies.
My name is Stephen Otfer. This is my second year in our Aerospace program within the UAV team, and I have prior industry experience with my role as software development in computer vision and system networking.
I am a member of the CS part of the AUVSI team. I work on object avoidance and interoperability. I'm in my 5th quarter at Clark College, and I've been in the aerospace club for about 3 months. I have no experience with UAS technologies, but I do have experience with the Python language, which we are using for our programs.
Okay, our vehicle this year is an octocopter. It is a 1200 millimeter frame powered by 8 340 kV Tera brushless DC motors, pushing 1855 carbon propellers. It is powered by anywhere from 2 to 4 10,000 milliamp hour 6S batteries, and each motor is controlled by 40 amp ESCs.
So the software for the ground control station is Mission Planner, and the release mechanism for the payload is a servo-actuated claw.
So the airframe has many 3D printed parts on it, from our battery mounts to our payload bay to a platform with a GPS module and a kitsock sits on the top. We also I did machine custom adapters to get our landing gear to fit correctly on there. We've also 3D printed other components for the landing gear as well.
The system operates by using Raspberry Pi to onboard vision processing, sending it over a Ubiquiti Rocket M5 down to a custom gimbal which was student designed and manufactured, and that houses a Ubiquiti Nano Station. This relays it over to our Linux laptop, which takes in the incoming data and also the data that's given in by the interoperability system. This is then distributed over to the mission planner to revise it for the other mission requirements, such as updating the course and also for the payload deployment. The classification itself is done using a TensorFlow neural network that is run on the Intel AI Dev Cloud for training using a generated data set combined of real pictures and computer-generated images to ensure that there is not overfitting, and it is deployed using an Intel NVIDIA's neural compute stick, so all of our computer vision system is operated on board the actual vehicle.
We will be attempting autonomous flight, obstacle avoidance, object detection, localization and classification, as well as air delivery, and are confident in our ability to complete all these tasks.
The autonomous flight portion of the mission will incorporate taking in the waypoints autonomously from the interoperability system through the Linux laptop and then passing it over to the mission planner to perform autonomous flight.
We have used a mission planner to perform 10 autonomous flights thus far, 5 of which required 0 pilot input. And each autonomous flight was about 8 minutes in duration. For our autonomous flights, we've attempted approximately 5 waypoints per flight with a 95% capture accuracy.
The obstacle avoidance system uses a RRT algorithm mixed with a line smoothing algorithm to optimize the performance by creating the shortest distance around any virtual objects that are submitted into it. The system has been tested many times using virtual objects in simulations and has proven very successful. It sends out the corrected path over to Mission Planner, which updates the waypoints in real time, and so that the UAV can avoid any virtual objects. The detection used by the UAV is an improved version of regional convolutional neural networks. Instead of using just selective search, which can be used for larger objects, it also uses the blob detection algorithm to find smaller objects. This means that as the UAV can descend and descend, it will not lose the objects based upon how large it is within the frame. After these subframes are extracted from a larger aerial frame, it is then evaluated through a smaller AlexNet that is implemented in TensorFlow and then developed on Intel AI Dev Cloud. After you've taken the model from training that was trained using Xeon scalable processors, it is then transferred to a Movidius neural compute stick, which can run the algorithm in real-time and with high efficiency and low power on board the UAV without the need to transmit any images to the ground station, thus reducing the amount of computation required considerably on board the vehicle. Comparing the data with the IMU, the altimeter, and the GPS on board the Raspberry Pi in the payload section, and the angle of the camera and the position of the coordinates of the subframe within the aerial image, we can extract an estimated GPS coordinates of each target after it is correctly identified. The images were trained off of a generated data set so that it will create enough variance so it does not overfit due to a poor lighting, differences of terrain, or differences of targets, also paired with real images taken by our UAV during our test flights. The model itself is quite powerful and can be re-evaluated to any data set which we give it, so we can use the exact same model to look for standard and emerging targets and be retrained for future missions.
We have so far conducted 8 drops of the payload from different altitudes, being 100, 200, and 300 feet. From 300 feet, we consistently hit within 10 feet of the target.
During testing, several flaws were exposed on our system. To begin with, we were initially running on 4 10,000 milliamp hour 6S batteries. This proved to provide a significant strain on the drive components of the UAS and subsequently led to the motor failure during landing on one of our flights. The UAS was fortunately capable of stabilizing itself and landing autonomously with only 7 motors. However, it was decided that from that point on, we'd be only flying with 2 of the batteries to reduce any future failures. We've also encountered significant electromagnetic interference from all the DC currents that are running past our electrical sensors, and have taken a number of steps to isolate these sensors and insulate them from any noise. We've had multiple compass and GPS failures, which have resulted in erratic flight, likely from this EM interference, which has been minimized or actually reduced or eliminated entirely as of now. We also suffered broken landing gear, once again from the added weight of the batteries. It turned out that the landing gear was, the design was insufficient to handle any sort of lateral motion on its descent. This was fixed by 3D printing reinforced brackets for the landing gear and has not been a problem since then. Additionally, this is a very large UAS system with 8 18-inch rotors, and on descent produces a significant amount of turbulence and vortices. This is an ongoing issue of maintaining stability during descent. So far we've I guess accommodated that issue by reducing our descent rate to, I believe, 1/2 meter per second on landing, and this has worked out so far to the point that we were able to land autonomously, consistently with almost every flight.
Challenges I've had with this project are that since a few of us started a bit late, we had to pick up where other people left off, but we overcame that with good communication with the prior members.
The main errors which we can find within the software system that could potentially harm the mission would be speed, classification, and networking. For speed, we optimize the Raspberry Pi, removing all graphical interfaces. So instead of working as a full desktop computer, it's an optimized single-board processor, and then we use movies to speed up all neural computations. For the classification itself, the dataset combines the real and generated images through applying Gaussian noise to all of them, so we can create millions of sample images from a handful of real images taken in the field. And for the classification, the network itself applies many different optimization techniques such as batch normalization, error regulation, and in Atom optimizer gradient descent. And then for the networking, in order for it to not create an error if it breaks a network by moving behind any sort of obstacles or moving out of range, instead of using a UDP or TCP socket to connect to the ground station, it instead uses a UDP method known as Open Sound Control, which can reliably prepackage information and send it over without the requirement of any IP address, but over a secure network